today's lesson is mostly about probability, but specifically it's about a contingency table, also called a two-way table, that you can see in this particular example. It's called two-way because there are two variables, in this case IQ and gender. Sometimes you may have 10 columns or 5 rows. It just depends upon the situation. In this case, we've got 3 columns and 2 rows. When you do have a contingency table question, one thing that I would encourage you to do is to label the rows and the columns with something easy that makes sense to you. I usually prefer single letters. I've occasionally used numbers. So for example, it makes sense to me to label this below for B and A for above, and then I'll choose M for middle. C for center would also make complete sense. Again, whatever works for you. And then it should seem reasonable that I'll choose F for female. One of the problems that I've created for myself is I cannot choose M for male because M is already the middle IQ scores. So I will choose F complement. And as you're going through these, I would recommend that you label what you're looking for. Most of these, as I said, are probability questions. Part A is asking for the probability a person is male. I call this a one-set question because it only asks about males. It doesn't ask about females or anything about IQs or anything else. So you're just looking for the probability that they're male. These are some of the easiest questions. Most of your denominator for this question will have 1,000 or whatever that total is. And of those 1,000, 480 are male. Part B, it is not a one-set question because it talks about IQ and gender, above 120 and male. So if it is a two-set question, then it will either be an and, an or a conditional. For ands, look for the keywords of and or but or both, something that's saying something and something else. For or questions, look for the word or nor. Conditional questions sometimes use the word given, but not all the time. This one doesn't use the word given, but it doesn't have any of those other key words, so I know it must be given. So either we have and given, above given male, or we have the probability of male given above. And the difference here is ands and ors, it doesn't matter what order you write them in. But with conditionals, it does. The one that goes after the bar is the one that is given, is the one that you know is true. Here in part B, this isn't just any old person. This is a person with an IQ above 120. So we're looking for the probability that it's a male given that the IQ is above 120. Now, since it's given A, we're only going to be using the A column to pull numbers. And we always divide by the total, and we know that the total in column A is 200. Oops, and I did in these two examples what I said I shouldn't do. I used M and I should be using F complement, which will make a difference later on. And of those 200, 96 are male. So we get another 0.48. Now, part C was nice because they flat out used the word given, so you know it's a conditional. Given that it's female, find the probability that the IQ is above 120. So this case, we're only going to be using the F row. And in the F row, there is a total of 520. And of those 520, 104 have an IQ above 120. Or 0.2. And again, that was because of that word given. In part D, they were nice and gave us the word and. So a high IQ and female. There are several ways to do this. There are some ways that are the hard way. If this were not a contingency table, I would definitely tell you to use the hard way. It's your only option. But this is a contingency table. There is a significantly easier way. We have 1,000 people total, and of those 1,000, 104, oops, pardon me, 104 have an IQ above 120 and are female. Much easier than the hard way. Part E, the probability of two things. It doesn't use and, but, or nor, so it's going to be a conditional. And it says if a person has an IQ above 120, so given that they have an IQ above 120, what is the probability that they are female? So we're only using the A column, and in the A column, 104 are female, or 0.52. Part F, another one that does two sets. It doesn't have an and, but, both, or nor, so it's going to be a conditional. So this isn't just any old person, this is a male. And we're looking for the probability that their IQ is above 120. So in the F complement row, there are 480 people, and of those 480, 96 have an IQ above 120 or 0.2. Now I still have two more probability questions left to come, but I want to point out that I did ask an awful lot of conditional, not because I think there's going to be an awful lot of conditional on the test or on the problem set or anywhere else, but I think that conditionals are the hardest to identify, that they are conditional, and they're the hardest to figure out, is it A given F or F given A? So I did practice with a lot of those, and that's one reason why this question is substantially longer than normal. In addition to being asked probabilities, you'll also be asked independence questions. Now, the three formulas for independence or I should call them tests because these are not formulas necessarily. If they tell you that some things are independent, and there are some questions in this chapter that do, then you do know that these three statements are true, but right now we don't know that they're independent. We're trying to prove that. So I'll put the question mark above them. It says, is being female and having an IQ above 120 independent or dependent? Another thing about independent questions, which may not seem too problematic right now, but will be by the end of this example, is except in rare circumstances, you should never use your common sense to answer this question. You should always justify, I called it here with a formula, one of these three tests, whatever you want to call it, to convince yourself, is it independent or dependent? We have already calculated here in part C the probability of A given F. So the probability of A given F, we can try to find out if that equals the probability of A. So 0.2, does that equal? So A, there's 1,000 people total, and 200 have an IQ above 120. And sure enough, 0.2 does equal 0.2, so they are independent. Here's where your common sense can get you in trouble. It would be really tempting to say, well, if that's independent, then part H is also going to be independent, because it's also asking about IQ and gender. Sometimes that is true and sometimes that is not. So we need to, again, show a formula. We have calculated in part A the probability of F complement. So we can find out, does that equal the probability of F complement given B? Now the probability of F complement given B, so we're only using the B column, so there's 250 total, and 110 are male. 0.48 does not equal 0.44, so these are in fact dependent. So while it turned out one pair were independent, another pair were dependent. Again, your common sense could have gotten you in trouble that way. Two more probability questions. Both of these, you'll notice, have the word or. We're going to use the addition principle. One of the things that's nice about a contingency table is we know that we're going to have a common denominator. And I've re-put the table at the bottom. I knew we'd run out of room. Sorry, that keeps happening. Get this dash out of my way. So the number of people in A are 200, plus the number of people in F are 520, minus the addition principle says we need to subtract out the people we've counted twice, which in this case is 104. So since J is also an OR question, but it has one very distinct difference. A and F were not mutually exclusive. There were people that have an IQ above 120 and are female. But there is no person that has an IQ above 120 and below 90. Not a single person that does. So we don't have to subtract off the intersection. We can just add A plus B pardon me, 0.45. And let's talk about this mutually exclusive. Unlike independence, you should use common sense to figure out if things are mutually exclusive. Are there people that have an IQ above 120 and are male? And you hopefully know some people like that in your life. So no. And for a lot of questions, this would be good enough, but I would argue on a contingency table, you can go further. Not only do you know that such people exist, but in this sample, there are 96 people like that. So a very long question, but again, hopefully this is anything that you could ever want to know about a contingency table. But of course, if you have questions, please feel free to ask.